works. So may I go with one example? Yes?
Yes, ma'am.
Yes. Right. So let us go with one example so that you can understand how actually this algorithm works. So we are considering a very simple neural network. So you may also solve this problem with me. Suppose this is my x0. x0 is always 1. This is x1 and this is x2. Let us assume that we are having only two inputs and this x0. So let us assume that x1 is 0.05 and x2 is say 0.1. We are giving the values, right, for inputs. So we are going to solve actually one problem. Let us assume that we are having one hidden layer. So I am having here this neuron H1 and this neuron H2. So two hidden neurons in hidden layer, and once again this is a bias or additional input, say 1. And let us assume that we are having two neurons in output layer, O1 and O2. Right? And this O1 is producing, or this is the actual output, 0.01 and 0.99. Okay, now let us see the connections. Every neuron or every input should be provided to every neuron. So this x0 from this x1 also I'll be having this, from this x2, sorry, right? Now from this h1 the input goes to O2, O1 and O2. From this H2 also the input will go to O1 and O2, right? And this one also goes to O1 and O2, right? Now, associated with all those links or connections, we are having the weights. So let us say that this is, here I am having the bias, say B1, and say bias is B2. And let us assume that this bias B1 is say 0.35 and this bias B2 is say 0.6. Okay. Now this link is having the weight W. So let us derive or abbreviate it like W from x1 h1. So W x1 h1. This link is associated with weight W x1 h2. This link W x2 h1 and this link W x2 h2. Now this link, let us say W h1 o1. For this link W h1 o2. For this link W h2 o1 and for this W h2 o2. So these are the associated weights. Okay. Now let us initialize weights. So let us assume that we are initializing those weights. So W x1 h1 is say 0.15. W x1 h2 is say 0.25. W x2 h1 is say 0.2, W X2H2 is say 0.3. Also WH1O1 say 0.4, WH1O2 is say 0.5, WH2O1 0.45 and WH2O2 is say 0.55, right? So in this network having two inputs, we are having two hidden neurons. So one hidden layer that comprises of two hidden neurons. We are having one output layer which also comprises of two output neurons, right? And we are having two biases here, right? So this is what we have, the network. Now we would like to learn, and we are going to make use of back propagation algorithm. So what are the steps in back propagation algorithm? Are initially, so step number one, initially what we are going to do is we are going to move in this direction, right? So to find out the observed output, right? So first step should be forward propagation. The second step is backward propagation. And the third step is putting all the values together and computing the updated weight value. So updation of weights. Right? Now, how we are going to learn? So let us begin with solving this problem. Have you understood how we have formalized this problem? Yes? Is there any doubt so far?
Ma'am, can you explain that steps?
Which steps? These steps, na? We are going to solve according to these steps now. So
Yes,
you
ma'am.
understand what we are going to do under each step. Right?
Yes, ma'am. You can continue, ma'am.
So now let us go to step number one. So what we are going to do in step number one? See, we are having here the inputs. Okay. So first of all, we are going to find out the inputs for these hidden neurons, H1 and H2. Right? So we are going to compute the net input for neuron H1. Net input for neuron H1. So how I am going to find it out? Net input for neuron H1. So I'll be computing it as net H1 is equal to, I have explained it earlier how I am going to compute this input for this neuron H1. I am having this X1 multiplied with this weight and having this X2 multiplied with this associated weight, and we are having this X0 which is 1 multiplied with the bias. So net H1 is computed as W x1 h1 into x1 plus this weight w x2 h1 w x2 h1 into x2 plus this is one more input which is 1. So bias, that is 0.30, sorry, so here we are having bias B1 into 1 x0. This is my x0, right? So if I try to solve this, what I'll get is 0.15 multiplied with this x1 is 0.05 plus x2 h1 is 0.2 into x2 is 0.1 plus b1 is 0.35 into x0 is 1. So if I compute this, I'll get 0.3775. So this is input for my neuron H1. Got it? Now, what I want to compute output for this neuron H1. So how I'm going to compute that? So output for H1 is now being computed. So let us denote it as out H1. As I stated, our activation function is, what is our activation function? Our activation function is the sigmoid function, right? So my sigmoid function is denoted as 1 divided by 1 plus e to the power this minus net h1. We have seen this expression earlier for sigmoid function. We have used this sigmoid function whenever we discuss logistic regression as well. Also in the last class, we have discussed this sigmoid function, right? So this sigmoid function is given as 1 divided by 1 plus e to the power this minus net h1 input to this neuron. Okay, so this is nothing but 1 divided by 1 plus e to the power minus 0.3775. Correct? So this comes out to be 0.59327. So this is how we have computed input for this neuron H1, hidden neuron, and output of this hidden neuron. Got it? So this comes under forward propagation, step number 1. So we are moving from left to right. Are you getting me? Yes? Are you getting me? Am I audible? Hello?
Yes, ma'am.
So are you getting me or not?
Yes, ma'am.
So what next we need to do? Under this step number 1, we have computed for this hidden neuron H1. So similarly, we need to compute the input for H2 and output of H2. Right? So compute now net input for H2 and output of H2 on the similar lines. Is it possible to do? Yes or no? Yes. Are you getting me or not? Are you getting me or not? Please respond. Are you getting me or not? Is it clear or not?
Yes, ma'am.
So compute now the net input for H2 and the output of H2. So I'm not going into these steps now. So after computing, you please do it on your own. After computing, what we will get is the net input for H2 is 0.3925 and the output of H2 comes out to be 0.59688. So you do it on your own. Okay. Now, what we are going to do next is we are going to repeat this process for our output layer neurons. So, in our output layer, we are having two neurons. So, this similar procedure we are going to follow for input for O1 and output of O1. Similarly, input for O2 and output of O2. Are you getting me? Yes? Are you getting me? What we need to do? We need to continue the same procedure for output layer. In output layer, I am having two neurons, O1 and O2. So what I need to do is, I need to compute the input for O1 and output of O1. Also, I need to compute input for O2 and output of O2 on the similar lines. And then after computing this, we are going to compute the error. So I hope now you must have got the idea how actually the multi-layer neural network learns, right? So in this example, what we are having is, we are having two-layer neural network. So this is the input layer that we have. We are having one hidden layer and one output layer. The respective weights we have assumed initially, right? We know the input and we know the output. We are trying to learn the training sample, right? So I hope you must have understood whatever we did in the last session. So we need to follow three important steps in back propagation. So first is the forward propagation. So what we mean by forward propagation is, from input to output, the input signal goes, right? And accordingly, we are computing the error at the output layer. As I stated, at output layer, we know the actual output and we know the observed output. So error can be computed at the output layer. But as at the intermediate layers, we do not know the actual output of these intermediate neurons. And that is why what we need to do is, as the output at or the error that we have computed at the output layer, the error of the previous layer actually is contributing into the error at output layer. So what we are doing is, we are back propagating that error. So we are computing the error at output layer, and as that error also includes the error from the previous layer, simply we are going to back propagate that error, right, in the reverse direction. So our back propagation actually works in reverse direction. So in this direction. Okay, and what we are simply doing is we are back propagating the error, we are computing the respective terms in back propagation, and finally we are going to update the weights, right? So unless we reach to the minimum error, we are going to repeat this process. So how to actually implement this process? We have seen the first step in this process of forward propagation, and that step is, see here what we did in the last class. The input is being provided to the hidden layers, right? So what simply we did, we computed the net input for each of the neurons at the hidden layer. So we computed net input for this H1, that is the hidden neuron. Also, we computed the output produced at this neuron H1. Similarly, we computed the net input for this H2, and also we computed the output of this hidden neuron H2. So we have followed the process. The activation function that we are using is sigmoid function. So while computing the output, we need to use the expression for the sigmoid neuron. And that is 1 divided by 1 plus e to the power the input. And that will give us the output at that neuron, right? So I hope you must have understood this process till this point. If you have any doubt, please let me know. Otherwise, we are going to proceed. Yes? Any doubt till this? May I proceed with the next?
No, ma'am.
So may I proceed with the
Yes, ma'am.
next? Okay. So we have
Yes, ma'am.
computed.
Yesterday, ma'am, you have told us to hello,
Compute the
ma'am.
next step. Correct, no? So I
Yes,
asked
yes, yes.
you to compute the input for O1 and output for O1. So whether you have done that?
Yes, ma'am.
Okay. So let's go through now that step. So we are computing output for O1, right? So while computing the output of O1, what we need to do is we need to compute the net O1, that is the input for O1, and then we need to compute the output of O1. So while computing the input of O1, what you did, these are the weights we know, right? So these are the connections. So H1 is connected to O1, H2 is also connected to O1, and these are the respective weights. So simply what we need to do is we need to use now this WH1O1 into output of this H1 is input to O1. Correct, na? So output of H1. So that we have computed in the earlier step. So out H1 into sorry, plus this weight WH2O1. So WH2O1 into output of this H2, that is input for my O1. So out H2 plus for this neuron I am having this bias B2 into 1. Okay, so this is 0.4. This we have computed as 0.59327 plus H2O1 is 0.45 into out H2 that we have computed in the earlier slide. So that is 0.59688. B2 we have assumed as 0.6. So this comes out to be 1.105905. And how we are going to compute now this output of O1? Here we are having the activation function, that is sigmoid function. So 1 divided by 1 plus e to the power this minus net O1. So 1 divided by 1 plus e to the power minus 1.105905. So this comes out to be 0.751365. So I hope you must have got the same result.
Yes, ma'am.
Right. So similarly, we are doing this for this O2 also. So we are computing net O2 using the similar steps, and this comes out to be 1.224919, and out O2 comes out to be 0.772928. Right? So this is the output of O2 and output of O1 is this. Correct? Now, what we are going to do is, see here, the actual outputs we know. So the actual output of O1 is 0.01 and actual output of O2 is 0.99. And what we have got? We have got the observed output of O1 as 0.751365 and the output for O2 is 0.772928. So simply what we are going to do is we are going to compute the error now. Okay, so we are going to compute the error. So error for O1 here. So let us assume that this error is denoted as error at O1, EO1. That is equal to half summation target minus observed output whole square. So here it is the only one output, so actually no need to have this summation. So half 0.01, that is the actual output, minus the observed output is 0.751365 whole square, and this comes out to be 0.274811. So that is the error for O1. Similarly, we are computing error for O2. and it is denoted as EO2. So it is half 0.99 minus 0.772928 whole square, and it comes out to be 0.02356002, right? So obviously the total error, if we compute, it is EO1 plus EO2. So 0.274811 plus 0.02356002. So it comes out to be 0.2983711. Right?
Ma'am,
So, yes.
is it necessary to take each every decimals? Means can we take up to 4 decimals?
Yes, we can. Right? So the precision, we may take up to 3 or 4 decimal digits, right? So this is
Okay,
how
ma'am.
we have computed this total error. Okay, now we are done with this forward propagation. We have computed the error, and now we are going to back propagate the error. Okay, so let us see now the step number 2, and that is the back propagation. So see here, what we are having is, we have computed this total error. Here we are having, so we are considering only one neuron for the sake of understanding. So here we are having output of O1, right? Here we are having input of O1, okay? And what we have here is B2. Then we are having here output of H1, that is input for the output neuron, and output of H2, that is also input for the output neuron. Okay, and what simply we are going to do is, we are going to back propagate this error here, and then we are going to back propagate that error into the subsequent layers. Okay, so what we are supposed to do is, let us consider now this weight. We want to update the weights, right? So let us see here with respect to this weight, WH1O1. So consider this WH1O1, and we would like to update this weight. Every weight we need to update, but for understanding, we are demonstrating here the process how this weight gets updated. So similar procedure need to be applied for updating all the weights. Okay, so let us consider now this weight WH1O1.
Ma'am,
Now, yes,
ma'am, here we should consider the each error. Why we are
yes,
taking the total error? Means
no,
error for two different is different now. Then why?
yes, see, I'm going to demonstrate it. We are computing the total. See, what we are trying to do is, we are having at the output layer, we are having different neurons, right? And every neuron is having some error associated. So obviously, this entire thing, the error, that is meant for the ultimate output of my neural network. So all those outputs actually together are describing my output of the network. See, I am having multiple neurons in the output layer. But collectively, whenever it comes to the output, the collective output of all the output neurons I am considering, right? So obviously, whenever I am computing the error, I am computing the total error of the neurons. So whatever is the error that is generated at output neuron 1, output neuron 2, and so on. So I am having lots of neurons, maybe. So error associated with every neuron is actually contributing in my actual total error, right? And whenever I'm saying that I want to minimize the error, which error I would like to minimize? I would like to minimize the total error. I'm not considering individual error that needs to be minimized. I want to minimize this total error, right? See, if I'm having such kind of a plot, then I need to reach to this minimum. Okay, so I need to take little steps. If I'm here, I need to take little steps to reach to this. If I'm here, once again, I need to take small steps to reach to the minimum. So whatever this plot is describing, this plot is describing the error, total error, not the individual error I'm going to minimize. I'm going to minimize the entire total error. And that is why we are considering E total, right? So every weight needs to be updated. So I'm describing only the process of updating this one weight. So the same process needs to be applied for every weight. Okay, so what I'm going to do next is I want to calculate rate of change of error with respect to change in this weight WH1O1, right? So obviously I need to consider now here the partial derivatives. We are going to make use of gradient descent, right? So we need to make use of the partial derivatives. So delta E total, what we want to compute is delta E total, partial derivative of my error with respect to the change in this weight WH1O1. WH1O1. Delta E total, so partial derivative of error with respect to this weight that I am considering right now, WH1O1. Now, this can be computed as the chain rule. We are not going into the derivation of this. I am simply giving you the formula. Okay. So, we are making use of the chain rule. So, partial derivative of E total with respect to this out O1. So, delta out O1 into delta out O1 divided by delta net O1. So partial derivative of out O1 with respect to its input delta net O1 into partial derivative of net O1 divided by this weight, actual weight WH1O1, right? So this is what we would like to compute. Now, since we are propagating backwards, we need to calculate the change in total error with respect to these two, O1 and O2, right? So once again, I am writing here the expression E total, that is half target of O1 minus out O1, actual output of O1 square plus target O2 minus out O2 square, right? So this delta E total, so I'm computing the derivative now with respect to with respect to out O1, derivative is minus target O1 minus out O1. So this is the derivative of this expression with respect to out O1. Okay, so we know all those values, so simply we are substituting those values. So 0.01 minus 0 point out O1 we have computed earlier, it is 75136507. So it comes out to be 0.74136507. So this is this first term that we have computed now, this first term. We want to compute the partial derivative of error with respect to this weight WH1O1. So this is the first term which is contributing into this expression. So we have computed that partial derivative of error with respect to out O1 and it comes out to be this. Okay, now what next? We are back propagating this, correct? So once again, what we are going to do next is we are going to calculate the change in output O1 with respect to its net input.
Ma'am,
Yes,
can you explain that last
yes.
term?
See here, this is my total error. Okay, total error is computed with this expression. I want to have a partial derivative of this term. Okay, so partial derivative with respect to, I am right now bothered about this O1. So partial derivative with respect to output O1, out O1. So simply what we have done is we have computed here this partial derivative of this term. We are not going into the mathematics. So partial derivative of this term comes out to be this. So simply by substituting the values, we have got this figure.
Yes, ma'am. But here we can also consider the target O2 minus out
Yes, we
O2.
are going to do that also. See, I am simply demonstrating only the one step, how to modify weight of this
Okay,
link.
okay, I got it. I got it.
Right? So same thing we are going to repeat for everything. For output of O1 as well as for output of O2. Okay? So right now simply for the sake of understanding, I am considering only one weight, this WH1O1, and how to update this. That's all. Okay? So we have got this term and now we would like to compute this term. Partial derivative of out O1 with respect to net O1, right? So how I am going to compute this partial derivative of out O1 with respect to net O1? So this is, I am simply giving you the formulae out O1 into 1 minus out O1. So these terms we have computed already. So this comes out to be 0.186815602. Similarly now what we are going to do is we would like to find out how much does the total net input of O1 changes with respect to this WH1O1. So we are going to find out how much the total net input of O1 changes with respect to WH1O1. So now we are computing. See here, net O1, we know the formula for net O1. It is WH1O1 into out H1. We have seen this earlier. Plus WH2O1 into out H2 plus B2 into 1, right? And what we want is, we want to compute the partial derivative of this net O1 divided by with respect to WH1O1. So this comes out to be 1 into out H1 WH1O1 plus 0 plus 0. So partial derivative of this with respect to WH1O1. So after computation, we get 0.59326992. Okay. So we have computed all three terms. See, partial derivative of out O1 with respect to net O1, partial derivative of net O1 with respect to WH1O1. So simply what we are going to do next is, sorry, I need to add one more slide, I guess. What we need to do is, we need to substitute it, right? So we are going for actual updation of weight. So step number 3. So what was our formula? Let us recall back. Partial derivative of E total with respect to WH1O1, and the chain rule we have applied. So partial derivative of E total with respect to delta out O1 into partial derivative of delta out O1 with respect to delta net O1 into partial derivative of net O1 with respect to WH1O1. We have computed all these three terms. So just by substituting those figures, (593269992). So by substituting these figures, we come up with this error with respect to WH1O1 as 0.082167,041. So this is the error with respect to this weight, WH1O1. Okay, now simply what we would like to do next is, we would like to update the weight. So how I'm going to update this weight? So WH1O1 now gets updated as WH1O1, that is the old weight, minus eta times this partial derivative of E total with respect to this WH1O1. So this WH1O1, the old weight was 0.4 eta. So let us assume now the eta value. So it is the learning rate. So let us assume that this eta value okay, and this term we have computed, and that is this 0.082167041. Okay, so after computing, the new weight comes out to be 0.35891648. So this is the new weight, this weight. So see here, after application of back propagation, we have computed, we have updated this weight. Okay, the similar procedure applies for every weight. Okay, so the similar procedure needs to be followed for WH1O2, WH2O1, WH2O2 and so on, and that too many number of times iteratively till we reach to the minimum error. Okay, so this is how actually the neural network learns from the training samples. So here we presented only one sample, right? So this procedure continues for all the samples in our training data set, right? And every time whenever we are presenting our training sample, it checks for minimum error and it repeats the process of updation of weights, right? So manually it is not possible to do that. Only why I explained you this process, because you should understand what actually is happening, that's all. Okay, and the same process continues for updation of all the weights. Here our neural network is very small, having only 2 hidden neurons and 2 output neurons. In practice, we are having very huge neural networks, and this entire process needs to be carried out. Right? So almost all the libraries are providing directly the functions for training the neural networks and the back propagation algorithm. So whatever procedure I described right now, that procedure has already been coded in those libraries. Okay, and simply whenever we use that library, it is possible for us to train our neural network. Okay, so whatever we have gone through is simply the algorithm that is working behind, right? So I hope you must have understood this process. So may I proceed? Yes?
Yes, ma'am.
Okay.